Hello. Okay, so good morning, everyone. Welcome to today's sixth session on chemical engineering thermodynamics. To till now, we have completed so many topics, and we are going to continue on heterogeneous closed system, where we will be deriving Gibbs phase rule. So for single component open system, we have derived that du is equal to TdS minus PdV plus mu dn, dH is equal to TdS plus VdP plus mu dn, dA is equal to minus PdV minus STT plus mu dn, and dG is equal to VdP minus STT plus mu dn, where we defined mu is equal to del U del N at constant S comma V, mu is equal to del H del N at constant S comma P, mu is equal to del A del N at constant V comma T, and mu is equal to del G del N at constant P comma T. Now, moving ahead to the heterogeneous closed system. So what is assumed when we are dealing with heterogeneous closed system? So it is assumed that heterogeneous closed system is formed by large number of homogeneous open systems. Those are bounded by a boundary. Okay, so in a boundary, in a closed boundary, there are various large number of open homogeneous systems available. That system we are dealing with, or we are calling it as a heterogeneous closed system. So let's say in this heterogeneous closed system, we are having pi number of phases. So phases varies from 1 to 2 up to pi, and that is denoted by alpha is equal to 1 to pi. And C is equal to components, and components, let's say it varies from n is equal to 1 to C. So for any heterogeneous closed system, we have seen that du at constant s comma v should be equal to 0. dH at constant s comma p should be equal to 0, dA at p comma t should be equal to 0, and dG at t comma p is equal to 0. Now, to derive this Gibbs phase rule, we use this particular relation du is equal to TdS plus TdS minus PdV plus summation I is equal to 1 to n mu I dni. So here why this particular relation is chosen. This relation was this phase rule was derived by Gibbs, and he chose this du is equal to TdS minus PdV plus mu I dni relation. So what can be the reason? The reason are S and V are extensive properties, and those are differential of, in terms of, in du S and V are differential of extensive properties, and P and T are intensive property. Those are coefficient of that extensive property. So it was chosen by Gibbs. Now to write this particular formula for pi number of phases and C number of components. So we write it like that: du is equal to, now one thing very important to remember, that when we are mentioning phases, it should be, we will be writing them in superscript, and when it is a component, we will be writing it as a subscript. So in any relation in this derivation, when something is in subscript, that means we are talking about components, and when something is in superscript, we are talking about number of phases. Okay, so for this, from this relation, okay, so let's write it down for pi phases and C number of components. So we write it like that: du is equal to, okay, it was first term is T into ds. So T and ds will be of particular phase, temperature of particular phase, entropy of particular phase. So we will write T alpha, ds alpha, and we will vary alpha is equal to 1 to total pi number of phases. So alpha is equal to 1 to pi T alpha ds alpha minus PdV. So similarly for pressure also, pressure of particular phase and volume of particular phase. So we will vary alpha is equal to 1 to pi number of pi phases, P of alpha and dV of alpha. Correct. Now in this term mu I dni, so we have I is equal to 1 to C components. Okay, so I is equal to 1 to C mu I dni, but those components will be present in both the phases. So we will need one more summation of alpha is equal to 1 to pi, and in superscript we will add alpha. So what is it? Chemical potential of each component first we added, and then chemical potential of each component then in each phase. So we write this particular equation to derive the Gibbs phase rule. Now let's try to expand this relation. So How do we expand it? So first, let's say I'm expanding for alpha is equal to 1. So how will I write? T1 ds1 minus P1 dV1 plus, okay, now here what is the issue? We have component 1 to C. So let's first write it for 1 mu1 dn1, then second component mu2 in phase 1 dn2 in phase 1 plus like that till we have mu c in dnc in phase 1. Okay, so we have currently written everything for one phase. Now we will move from writing this equation for alpha is equal to 2. So we will add plus 2 T2 ds2 minus P2 dv2 plus, now here two summations. So let's first write it for component 1, 2 and 3 till C for phase 2. So mu1 in phase 2, dn1 in phase 2 plus mu2 in phase 2, dn2 in phase 2 till we are reaching at mu c in phase 2, dnc in phase 2. And this relation we can write it down for, we have written for pi, alpha is equal to 1, alpha is equal to 2. Like that we can write it for alpha is equal to pi. So what will it be? T of pi ds of pi minus p of pi dv of pi plus similarly mu1 of pi dn1 of pi plus mu2 of pi dn2 of pi plus up to mu c of pi dnc of pi. And for this heterogeneous closed system, we see that du of s comma v should be equal to 0. So this whole relation must be equal to 0. So in this particular equation, how many variables we are having? Okay, so we see that in each equation there are there are C components. This C number of components, total C components. So these are C relations plus this one TDS and PDV. So C plus two variables, and this was for one phase. So this these relations for total pi number of phases. So we are having total pi into C plus two variables in this above equation. Okay. So this one equation has this C components plus these two additional TDS and PDV. So this is pi plus, sorry, this is C plus 2, and there are total pi equations. Pi phases, there are pi phases. So there are total pi equations 1, 2, 3 up to pi. Okay, so we are having total pi into C plus 2 variables in this above equation. Okay, so for this heterogeneous closed system, this du should be equal to 0 that we are that we defined. Now there will be some constraint that when we are dealing with SV, so this total ds should be equal to 0. So that is ds1 plus ds2 plus up to ds pi should be equal to equal to 0. Similarly, dv is equal to dv1 plus dv2 up to dv pi, those terms should be equal to 0. And similarly, dn1 plus dn2 plus dnc for each phase, alpha is equal to 1 to n, dni of alpha should be equal to 0. So let's say I'm writing for dni1, dni2, dni3, so on should be equal to 0. Okay, here it should have, okay, yeah, so it's correct. So how many constraints we have? We have total, for each component we have the C equations and additionally these two. Okay. Sorry, how this constraint is written? Yeah, dn1 in all phases should be equal to 0. So dn I in phase 1 plus dni in phase 2 plus dni in phase pi should be equal to dn for each component, when similar to where we say that summation of x mole fraction should be equal to 1. Similar to that, summation of that change should be equal to 0. So that's why for each component in each phase, so I am writing dn1 in phase 1 plus dn1 in phase 2 plus dn1 in phase pi should be equal to 0. So this relation can be written for each component. Okay, so there are total C components. So we have total C, this C plus 2 constraints. So how many independent variables we should have? We should have pi into C plus 2 minus of C plus 2. Now, so what can we do? We can express the equation of du in terms of not this uh, pi into c plus 2 variables, but pi minus 1 into c plus 2 number of variables. Why minus? Why there is pi minus 1? Because when we are replacing, let's say ds1 will be equal to minus ds2 plus ds3 plus up to so on, minus dv1 is equal to minus dv1 is equal to minus of dv2 plus dv3 up to so on, and dni1 is equal to minus of dni2 plus dni3 up to so on. So when we replace these, so let's say this was my original equation that I wrote earlier. So what I am supposed to do, I am supposed to first replace ds1 is equal to minus of ds2 plus ds3 plus ds4 up to so on. Similarly, dv1 I can replace as minus of dv2 plus dv3 plus up to so on. So like this, when I will replace it, so what will I have? Let's say this term is minus T1 ds2 and here it is plus T2 ds2. So can I write T2 minus T1 in ds2? Similarly, minus of here we will have P2 minus P1 into dv2. Similarly, plus of mu2 in phase 1 minus mu1 in phase mu1 in phase 2. This term mu1 in phase 2 minus mu1 in phase 1 into dn1 2 plus up to mu c in phase 2 minus mu c in phase 1 dnc 2. Similarly, for T3 term, I can also write it down as T3 minus T1 into ds3 minus P3 minus P1 into dv2 plus mu13 minus mu11 into dn13 up to so on. And similarly for pi phase, t pi minus t1 of into ds pi minus p pi minus p1 into dv pi plus mu1 pi minus mu11 of dn1 pi. Similarly for cth component, mu c pi minus mu c1 into dnc1 is dnc pi is equal to 0. Now let's say, not let's say, this entire expression is equal to 0 that we check. So when this entire equation will be 0, the entire equation will be 0 when all these coefficients are equal to 0. So I can write that T2 minus T1 equal to 0, T3 minus T1 is equal to 0, and T pi minus T1 is equal to 0. Similarly, P2 minus P1 should be equal to 0, P3 minus P1 should be equal to 0, and P of pi minus P1 is equal to 0. Similarly, mu1 in phase 2 minus mu1 in phase 1 equal to 0, mu1 in phase 3 minus mu1 in phase 1 equal to 0, and mu1 in phase pi minus mu1 in phase 1 should be equal to 0. Similarly, we can write this equation for all components. So for the cth component, mu c in phase 2 minus mu c in phase 1 equal to 0, mu c in phase 3 minus mu c in phase 1 equal to 0, and up to mu c in phase pi minus mu c in phase 1 should be equal to 0. Now, what do we get from here? This du equal to 0. So what do we get from here? We get that T1 is equal to T2 is equal to T pi. What can we write from here? T2 is equal to T1. Here T3 is equal to T1 and here T of pi is equal to T of 1. So what can we write? T1 is equal to T2 up to T pi. So in all phases, temperature must be same when it is in thermodynamic equilibrium. Then from here, what can we write? P of 2 is equal to P of 1, P of 3 is equal to P of 1, and P of pi should be equal to P of 1. So what can I write? P of 1 is equal to P of 2 is equal to up to P of pi. Now similarly, this is the condition for mechanical equilibrium. This was condition for thermal equilibrium. And what else we can write? We can write that mu1 in phase 2 is equal to mu1 in phase 1. Mu1 in phase 3 should be equal to mu1 in phase 1. And mu1 in pi phase should be equal to mu1 in phase 1. So what can we write? We can write it down as mu1 in phase 1 equal to mu1 in phase 2 is equal to mu1 in pi phase. And this can be written for all number of components that chemical potential should be equal in each phases. So I can write it down as mu c in phase 1 equal to mu c in phase 2 is equal to mu c in pi phase. So this is the condition of thermodynamic equilibrium that we accepted in our first lecture, and that is what we derived, that temperature should be equal in each phases, pressure should be equal in each phases, and chemical potential of each component should be equal in each phases. Okay. So now, what do we do now? So we have pi into c plus 2 variables, but s, t and mu we cannot vary independently according to Gibbs-Duhem equation. So we will have, we all three we cannot vary independently. This we have seen in previous classes, Gibbs-Duhem equation. So that says that we cannot vary T, S and mu independently if we are fixing two, other is automatically fixed. So we will have not pi into c plus 2 variables, but we will have pi into c plus 1 variables. Okay. And how many relations? Pi minus 1 into c plus 2 relations. So number of degrees of freedom will be this pi into c plus 1 minus this pi minus 1 into c plus 2. So when we expand it, we get it as pi into c plus pi minus pi into c minus 2 pi plus c plus 2. Okay, so this gives us that Gibbs phase rule, that is c minus pi plus 2. Okay, so this is what we have studied, or we have already known what is Gibbs phase rule, but in this class we have derived what is Gibbs phase rule and we have derived the condition of thermodynamic equilibrium. So what is condition of thermodynamic equilibrium? Temperature of, let's say there are pi phases. So in each phase temperature should be equal. Then let's say there are pi phases, then pressure of each phase should be, in every phases pressure should be equal. And let's say there is one component. So for that one component, chemical potential should be equal in all pi phases. And there are, if we are having C components, so for all C components, we should have equal chemical potential. And this gives us the derivation of thermodynamic equilibrium and Gibbs phase rule, that is F is equal to C minus pi plus 2. Okay, now we derived, or Gibbs derived, this equation based on only these combinations where S and V is differential of extensive properties. This differential is extensive properties and its coefficient is intensive properties. So Gibbs derived it for that combination also, that combination only. But this equation, this can be derived for all this, from all these thermodynamic relations, that dH is VdP, sorry, dH is this equation TdS plus VdP plus mu dN, dA is minus PdV minus SdT plus mu dN, and dG is equal to VdP minus SdT plus mu dN. So from all these, all four relations, these equations can be, this Gibbs phase rule can also be derived, but Gibbs did it for du equation. The reason is only that differential is extensive properties and its coefficient is intensive property. So it is easy to deal with the equations. Okay, so now this was all about Gibbs phase rule. Okay, so numericals will come at the end. So now we know that this relation dG is VdP minus. Okay, so till now what we did, we derived the single component, this single component open system equations, then multi-component open system equation, where we added here summation I is equal to 1 to n, mu I dni is equal to 0. And then we had a look at this heterogeneous closed system which is in various phases present. Okay, so this thing you have already studied, but let's try to do it. So when we are calling a phase, so what is phase? So phase is a part of system which is uniform throughout in composition and physical properties. So for each phase, composition and physical properties remain uniform throughout. Phases can be in the thermodynamic properties in particular phases are either identical or they vary continuously from point to point. Phase is something that is separated from the rest of the system by a boundary surfaces where the properties undergo a discontinuous change. And single phase systems are basically called homogeneous systems, and systems with more than one phases we call it as heterogeneous system. And from this phase rule, we say that number of components are required, minimum number of components required to define the system. So let's say I am dealing with water with its vapor. So I am only dealing with one component, that is water, but it is present in both the phases. liquid and vapor. So when I am dealing with that kind of problem, I need to fix one variable that can be either temperature or pressure. We cannot fix both temperature and pressure together. Let's say I'm dealing with normal water at room temperature. So for what water is one component and it is only in liquid phase, so phase is also one. So we say that degree of freedom is two. So we can define two variables, temperature and pressure. So we say that the density of water at 298 degrees Celsius, 298 Kelvin and 1 atmospheric pressure is some value. That some value is function of two variables, temperature and pressure. But let's say when we are saying that boiling point of water is 100 degree, its normal boiling point of water is 100 degrees Celsius. So for that, it is fixed at 1 atmospheric pressure. Okay, so this is what we did till now. So now we will move ahead and we are going to look at the concept of fugacity. That is really important concept in chemical engineering. Okay, so we know that dg is equal to vdp minus sdt. So can I write that del g by del t at constant pressure will be equal to minus s, and del g by del p at constant temperature will be equal to v. So this is my first order transition, and if I am doing one more transition, that is del square g by del t square at constant pressure, that is nothing but minus of del s by del t at constant pressure. And in our earlier class 2, we have seen that this del s by del t at constant pressure is nothing but Cp by T. So this is my second order transition. Further, if I do del T of this del G by del P at constant temperature term, so I get del V by del T at constant pressure, and that is nothing but beta into V. This is also we have seen in the previous classes. Okay, so let's say I'm dealing with extraction of acetic acid from toluene using water as a solvent. So what is going to happen? Water and toluene, they don't like each other. So water and acetic acid will be dissolved in each other and toluene will be separating out. Okay, so how can we say that how many or what is the composition of acetic acid in both the phases? One is solvent rich phase, that is toluene rich phase, and second is aqueous phase, that is water rich phase. So how much acetic acid is distributed between liquid phase and vapor phase? And in other way, the question is framed as how much acetic acid can be extracted using this particular process. So for that, we need to say that when chemical potential of um, acetic acid in, let's say, aqueous phase is equal to chemical potential of acetic acid in toluene solvent rich phase, we say that uh, till when this process is going to occur, till when V1 is equal to mu2, this transfer of acetic acid from aqueous phase to organic sol, sorry, transfer of toluene from aqueous phase to toluene rich phase is going to occur. So I'm just saying that this will happen till chemical potential of each component is same in each phase. But I'm just saying it is chemical potential. So how am I going to calculate chemical potential? It's not easy. Chemical potential is something abstract quantity. So can I relate my chemical potential to something physically measurable quantity? So for that, what we are doing, this equation, when I'm writing it at small g, that is partial, uh, molar Gibbs free energy, not partial, molar Gibbs free energy del G by del N. So that is nothing but mu. So when I write d mu is equal to VdP minus S dt at constant temperature, so I will be just left with d mu is equal to V into dP. Okay, so for ideal gas, this is specifically I'm writing for ideal gas. So ideal gas d mu is equal to RT by P into dP. So it is nothing but RT into ln differential of ln P. So when I'm integrating these equations on both the sides, I can write it down as mu2 0 minus mu1 0 is equal to, I need to integrate this equation from P1 to P2, RT into differential of ln P, that is nothing but RT ln P2 by P1. Okay, so what we did under isothermal conditions, when we are only dealing with isothermal condition, that is the condition at constant temperature. So the change in this abstract thermodynamic quantity is a simple logarithmic function of physically real quantity, that is pressure. So what I did, I converted this abstract thermodynamic quantity. How can I measure? I can measure it in terms of logarithmic function of something physically real or physically measurable quantity, that is pressure. Okay. So this equation relates a mathematical abstraction to the common intensive property of real world. This is something abstract. This is something real. So this mu and p are related with this particular equation. But I wrote this equation only for real gases. Okay. What I wrote, I wrote this equation only for ideal gas where I replaced V is equal to RT by P. But let's say I am now dealing with real gas. And let's say I'm writing this real gas equation with for equation for real gas with by using real equation of state. So what can I write? I can write it down as PV by RT. This is a real equation of state that we have already looked at, is equal to 1 plus B into P plus C into P square. This is what we have looked at. So what do I need to do? I need to replace in this equation V dP. I need to put a value of V. So my d mu is equal to my V will be equal to from here RT by P plus RT into B2 of T, B2P of T plus RT into B3P of T into P up to so on. So when I'm integrating this equation from 1 to 2, I need to integrate this whole equation. So what we are getting? We are getting, if I integrate it from P1 to P2, so it will be RTLN P2 by P1, or let's say first step by step integration 1 to 2 RT. RT I'm taking common because it is in all terms. So I'm writing it terms of RT is common, integration of 1 to P dP by P plus integration 1 to P B2P of T into dP plus integration 1 to 2 B3P of T into P into dP. Okay, so let's say I am integrating this. So what will it be? RT ln P2 by P1 plus RT B2P of T, and integration of dP will be P, and that will be P2 minus P1 plus RT B3P P2 square minus P1 square by 2 up to so on. Okay. So for real gases, so what do we see here? This first term RT ln P2 by P1, that term is of ideal gas term, plus there are some non-idealities added by other pressure term. Okay. Now we know here that this B2P, B3P, all are going to be different for all different gases. So what do we do instead writing these equations for real gases? We try to simplify it in some other way. We write this equation d mu is equal to RT into d of ln P. We wrote it for ideal gas, and I just want to maintain this function or expression like this only. So what I am doing for any real gas, I am writing it as d mu is equal to RT into d of ln F. So I am defining one term F that is dealing with non-ideality in dealing with pressure terms. Okay. So my what does this DLNF is? DLNF is this whole term. Okay. DLNF is nothing but DLNP plus B2P of TDP plus B3P of TP into DP. This whole term I am replacing it with DLNF. Okay, so d mu is RT into DLNF. So my mu I minus mu I 0 is equal to RT. If I integrate from zeroth state to some zeroth state to some state of interest, so I can write it down as mu I minus mu I0 is equal to RT ln Fi by Fi0. Okay. So what did Lewis did? This was derived by Lewis. So defined by Lewis for an isothermal change for any component in the system, whether it is solid, liquid or gas, whether it is pure or mixer, whether it is ideal or real, we can use this equation to estimate the chemical or to relate the chemical potential from fugacity. This F is called fugacity. In Latin, fuga is a Latin word which means that flight or escape. This we will come later when we are interpreting what really fugacity mean. So whereas my pressure will tends to zero. So what is going to happen? My gas is going to behave ideally. So my reference state can be ideal state. So for pure component, limit P tends to zero. My what should be my ratio of F by P? F by P should be 1 as my pressure tends to zero because gas is going to behave ideally, or my F tends to P. And for mixture, let's say for mixture of various components. So in various components, we will have fugacity of each component and mole fraction of each components present in the mixer. So what can I write? I can write it down it as limit P tends to 0, Fi fugacity of ith component divided by phi I fugacity of ith, composition of ith component in the mixer into P should be equal to 1. So what I am doing, I am defining my F by P as fugacity coefficient, but when I am not dealing, but when I am writing F by F0, I am calling it activity. So what is activity? Activity means how active a substance is relative to its standard states. And this provides a measure of the difference between chemical potential at the state of interest to its standard state when I am writing in terms of zero. Okay. Standard state temperature must be same as that of the state of interest, while pressure and composition need not to be same, because this thing we are dealing at, this fugacity is measured at isothermal condition. We have already mentioned earlier it should be isothermal condition. So temperature should be same for reference phase also. Okay, so how to choose about this reference phase? So that we will see now. So we had a look at d mu is equal to RT into differential of ln F, that is at constant temperature for any system and for any states. D mu 0 is RT into d ln P for ideal gas pure component system. And I can write it down as RT ln differential of ln F by P, or ln mu by mu 0 can be written as RT ln F by P, or mu by mu 0 can be written as RT ln F by F0. So standard state of mu 0 and F0 should be same. This is important. When we are dealing with this equation, it should be same. I'm not dealing when I'm not taking my standard state at ideal state, ideal gas state. So whatever state I'm choosing, it should be same for computation of both these and these terms. Okay. So how to choose a particular standard state? So for gas phase, pure component gas in its ideal state at 1 atmospheric pressure and system temperature, we can choose it as ideal gas. Or for pure component gas, we can choose at any temperature and pressure which we are working. That can also be chosen at standard state instead of 1 pressure, 1 atmospheric pressure. And this is basically used in vapor liquid equilibrium study of pure component or mixer systems. Okay, now when I'm dealing with liquid phase, so pure component in liquid state at 1 atmospheric pressure, then pure component in liquid state at system pressure, that is also basically used in study of vapor liquid equilibrium. Okay, for solid, pure component in solid state of 1 atmospheric pressure. So what is the importance of this particular equation? So this equation we can use for any phase, whether it is solid, liquid or gas. So that is the strength of that equation. I can use it for solid phase, liquid phase or gas phase. I can use it for pure component or mixtures, and or even I can use it for ideal conditions, or when I'm dealing with ideal gas or real gas, or ideal solutions or real solutions. So this equation remains as it is. So that is the strength of this equation. So let's try to define or understand fugacity. So why did we use fugacity term? So because it was difficult to visualize chemical potential, but the concept of fugacity is more easily convinced as corrected pressure, which for a component in a mixture of an ideal gas is equal to its partial pressure of that component. So it is a corrected pressure. Okay. And why these corrections are appearing? These corrections are basically due to non-idealities which can be interpreted by molecular considerations. Okay, so this non-idealities, sorry, this term of non-ideality, that is what it is being considered in LNF. So it is a measure of non-ideality of a gas. And relationship between fugacity and chemical potential is of conceptual aid in translating from thermodynamics to physical variables, where we are we are transforming this mu, that is abstract quantity, to pressure, that is real world quantity. So we are what it was written, abstract quantity is a simple logarithmic function of physically real quantity pressure. So this is how we are dealing with fugacity. Now we have now seen the fugacity, but how can we estimate the fugacity? Okay, just ahead we had a look that this is the condition of thermodynamic equilibrium, that is temperature in all phases should be equal to zero, pressures in all phases should be equal to zero, and chemical potential of each component in each phase must be equal to same. If I said zero, that is wrong. Temperature should be same in each phase, pressure should be same in each phase, and chemical potential of each component should be same in each phases. Okay. So we had this thermodynamic equilibrium conditions in terms of temperature, pressure, and chemical potential. But now what I have done, I have replaced my chemical potential with fugacity. So how can I, what will be my this equilibrium condition in terms of fugacity? So let's try to derive that. Let's say I am having one component which is present in two phases, alpha phase and beta phase. I am having one component which is present in two phases. One is alpha phase and one is beta phase. So from here, we know that mu of component 1 in alpha phase should be mu of component 1 in beta phase. So that is what is written, mu alpha is equal to mu beta. Now, how can I replace mu alpha? We had a look, mu alpha is equal to mu 0 alpha plus RT into ln f alpha by f0 alpha. And similarly, how can I replace mu beta? So mu beta can be replaced as mu beta is equal to mu 0 beta plus RT into ln f beta divided by f0 beta. Okay, so if I take the difference between these two, so what will it be? Mu alpha minus mu beta is equal to mu 0 alpha minus mu 0 beta plus RT into ln of f alpha by f0 alpha minus, if I take the difference between these two, so mu alpha minus mu beta, here mu 0 alpha minus mu 0 beta, and here RT ln f alpha by f0 alpha minus RT ln f beta by f0 beta. Okay, so let's say I'm dealing with only one component. Okay, so for that one component, my standard state is going to be same. Let's say I'm taking 298 as my standard state, and as component is only one. So for both the phases, this mu 0 alpha is going to be equal to mu 0 beta, and similarly f0 alpha is going to be f0 beta. Okay, so what can I write now? As my mu alpha is equal to mu beta, so this is equal to 0. Mu 0 alpha is also mu 0 beta, so this is going to be 0. So we are only left with RT ln f alpha by f0 alpha into f beta by f0 beta divided by f beta. Now f0 alpha is also equal to f0 beta, as we are dealing both pure component, one component at both at same standard state. So this term cancels out. So we are only left with 0 is equal to RT into ln f alpha divided by f beta. Now, these terms will be equal to 0. So, what can be 0? Can R be 0? Universal constant can't be 0. Can temperature be 0? In this case, it can't be 0. So, RT term can be 0. So, we are only left with ln of f alpha divided by f beta should be 0. So when this term is 0, when it is ln 1 is 0. So when it is ln 1, when f alpha is equal to f beta. So fugacity of component, each component in each phase should be equal. Okay. So that is the derivation of thermodynamic equilibrium in terms of fugacity. So we say that temperature in each phase should be equal, pressures in each phase should be equal, and fugacities of each component in each phase must be equal. So this is the modified thermodynamic equilibrium conditions in terms of fugacity. Okay. Now, while equality of fugacity in all phases signifies chemical equilibrium, the condition that activities must be hold equal holds only for the special case where standard state in all phases are same. In that case only we can write that activity is same. So ai is my fi by fi0 and my phi is fi by p. When my fi0 will be equal to p, standard state as total pressure of the system, in that case my activity will be equal to fugacity coefficient. Okay. Okay, so now when we were dealing with chemical potential or molar Gibbs free energy, we had a look at its effect on temperatures and pressure. So same thing. Now the same thing we are going to do for fugacity also. We are going to see how fugacity varies with temperature and pressure. Okay, so what was my equation? My equation was d mu was RT into differential of ln F, which is equal to VdP minus STT. So RT into del ln F by del P at constant temperature, which is equal to del mu by del P at constant temperature, and this whole term is equal to V. Okay. When I'm differentiating with respect to constant temperature, so it will be just V term. So del ln F by del P is equal to V by N at constant, V by RT at constant temperature. So if I'm integrating this equation, so what am I going to get? So this term ln F, F0 to F, so ln F by F0 is equal to dP will be this side integration 0 to P, V by RT dP. This is how I can write down my equation. Now my d mu is RT into differential of ln. That is what I actually wrote, but we are now in writing in terms of d mu. Okay, so d mu was RT d ln F. So RT into integration F0 to F differential of ln F will be equal to mu0 to mu d mu. So RT into ln F by F0 is equal to mu minus mu0. So what can I write? Mu by T minus mu0 by T is equal to R into ln F by F0. So when I'm going to differentiate this equation with respect to temperature, so I will have R into del by del T of ln F by F0, that is equal to del of mu by T by del T minus del of mu0 by T at del T. Okay, so what is this term? This we have looked at. So this is nothing but minus h by t square, and minus this term is as it is at mu0, so it is my enthalpy should also be at some standard state. So that is going to be equal to minus h0 by t square. So we will be left with the equation as del of f by f naught by del t at constant p comma n will be equal to h0 minus h into r will be here, so rt square, where h0 is my molar enthalpy at low pressure or ideal case condition. Basically that is nothing but integration of cp0 dt, and h is my molar enthalpy at interest of pressures. Okay, so what is my h minus h0? Increase in enthalpy due to expansion from pressure p to p0, from p0 to p. Okay, so this is the effect of temperature. Now let's try to understand the effect of pressure. So for real gas, again I am writing this relation. D mu is R into T differential of ln F, that is VdP, and for ideal gas d mu 0 is RT d of ln P, that is RT by P dP. So can I write it as differential of mu minus mu0 is equal to integration P is equal to 0 to my system pressure P, RT into differential of ln F by P. Okay. That is nothing but VdP minus RT by P dP. So that is V minus RT by P into dP. Okay, so I can write it down as mu minus mu0 is equal to RT into ln F by P, which is equal to integration. So here mu is also related and F is also related. So I can write it down as integration 0 to P VdP minus integration 0 to P RT by P dP. So what is this VdP term is saying? VdP term is saying that we need to know we need to know the behavior, PVT behavior of gas. Okay. And that we have already looked at using various equations of states like van der Waals equation of state, Redlich-Kwong equation of state, SRK equation of state, Peng-Robinson equation of state that we have already studied in our lecture where we defined or where we discussed the PVT behavior of gases. Okay. So if I do some kind of substitution, so I get my equation as ln F by P, which will be equal to Z minus 1 upon RT integration V infinite or V0, that is ideal gas equation, ideal gas volume minus V0 to V into dV. So this equation can be used for used when, let's say, I want to derive now, I want to replace this dV for various kinds of equation of states. Okay, so that can be done. So let's see here, I have already done that. So for van der Waals equation of state, we see that ln phi is equal to Z minus 1 minus ln of P into V minus B by RT minus A by RT V. Similarly, for Redlich-Kwong equation, ln phi is Z minus phi is nothing but F by P. So ln phi is equal to Z minus 1 minus ln of Z minus B minus A by BRT ln Z by Z plus B by Z, where B is nothing but small VP by RT. Similarly, for SRK equation, this term ln phi is equal to Z minus 1 minus ln of Z minus B minus A by BRT ln Z plus B by Z, where again here B is BP by RT. And similar equation we can write it down for Peng-Robinson equation of state, where Z minus 1 minus ln of Z minus B minus A divided by 2 root 2 BRT ln Z plus capital B 1 plus root 2 divided by Z plus B 1 minus root 2. So when I want to solve this equation, what will I do? First, I will solve for Z using equation of state. I will put that value of Z here for liquid and vapor phases, and we will see that if phi of liquid and phi of vapor is coming same or not. If it is not coming same, we need to change we need to reiterate this process. We need to change the Z, and we need to find the condition where phi 1 is equal to phi 2. So that will be our composition of vapor liquid equilibrium. Okay, so this is how we can use Fugacity coefficient, uh, or Fi cap is equal to F of Fugacity of each component in each phase should be equal. So that can be done by this particular equation of state approach, and we can find various thermodynamic properties. Like from here we can estimate volume, so volume will give rise to density. Then we can also estimate from volumes, we can also estimate enthalpy of vaporization, that also we have studied. From here, we will also find the vapor pressure. So that will also give us the idea of boiling point temperatures and various pressure conditions. For pure component, I'm just talking about right now. Okay. So this is really important thing to estimate fugacities of each component using equation of state approach. Okay. So now let's try to. So what else approach we have looked at? So we have also looked at compressibility factor approach. So my earlier equation was RT into D of ln F by P is equal to integration 0 to P V minus RT by P dP. So my differential of ln F by P will be integration 0 to P V by RT minus 1 by P dP. Let's say I'm multiplying here with P and dividing by P. So I will have PV by PRT minus 1 by P dP. So what is PV by RT? Z. So this is Z minus 1 by P dP. My F by P is nothing but phi. Okay. So I can write it as phi. Now let's say I want to write these equations in terms of reduced properties. So what can I write? PS PRPC. Here also PS PRPC. So PC is constant, so PC will come out and PC cancels out. So we will only left with Z minus 1 PR, Z minus 1 divided by PR into dPR. So we say that phi is function of Z comma PR. But what is Z? Z is function of TR comma PR. So we say that phi is function of TR comma PR, which is obeying the two parameter law of corresponding states. So from this, we can estimate the value of Fugacity coefficient. Similar thing we can do with picture correlation, where we write that ln phi is equal to ln phi naught plus omega into ln phi prime, or we can just write as phi is equal to phi naught into phi prime raised to omega. So if you charts are available, so if you look at this book, let's try to. Yes. These are for Z0. And see, this is phi 0 and phi 1. So if you know value of PR and TR, you can estimate this directly like this. Phi is equal to phi 0 into phi prime raised to omega. So you just need to know the component. Let's say I am dealing with methane. So methane will have separate value of omega, and what temperature and pressure I am dealing with respect to its critical temperature and pressure. That is what we need to know. So let's say if I am knowing the value of PR as 0.4 and value of TR as 1. So what will I have? I will have phi 0 value as 0.9727, phi 1 value as 0.9727, and my phi 0 value is something 0.8690. So this is how we can use these tables for various temperature pressure conditions. Okay, so this is very important to know and use. We will see some numericals based on this concept on how to use these charts in next class. So this will keep for next class. Now, there is one more approach to find this F by P term, that is residual volume approach. So how do I write it? I write it as RT into differential of ln F by P is equal to integration 0 to P V minus RT by P dP. So my ln F by P is equal to 1 upon RT integration of what is this V minus RT by P term. V is my actual volume and RT divided by P is my volume occupied if the gas were ideal. So what can I write? I can write it down as V minus V0 into dP. And what is my V minus V0? V minus V0 is nothing but my residual volume or departure function of volume. Okay, but for this to integrate 0 to P, I need to know the entire pressure range is required for PVT behavior of gas. So when I plot this V of R versus P and I take the area under the curve, and it when I divide it with RT, it will give me the idea of ln F by P, or it will give me the idea of Fugacity coefficient. Okay, this was one approach. Now other approach is this: from enthalpy and entropy residual functions also we can estimate these terms. So let's try to have a look at that part. So I can write it down as mu is equal to H minus Ts. So I can write it down as d mu is equal to dH minus Tds, which is equal to RT into differential of ln. So RT into integration F0 to F differential of ln F is equal to integration H0 to H dH minus T integration H0 to S ds. So ln F by F0 is equal to H minus H0 by RT minus S minus S0 by RT. So H minus H0 is HR and S minus H0 is SR. So if we know this thing, then also we can directly estimate it. And we have already seen how to estimate residual volume, residual this term. So HR by RTC is equal to HR0 by RTC plus omega into HR 1 by RTC. So if we know that terms from this Lee-Kissler relation, we can estimate HR by RTC, and we can just put it HR0 and HR1 like we can calculate for HR0 term, HR1 term, and then we will have HR by RTC, and from that we can calculate the value of HR, and that HR we can put it here. Similarly, same thing we can do for SR0 by R and SR1 by R for various conditions. And from this also, we can directly estimate the value of phi. Okay. Now, till now we looked at how to estimate fugacity of each component, or F by P. How should we do it? So we just try to simplify it, and first we try to have a look at how can we derive it, or how can we derive it using some simplified form, and then we converted it into term of this equation of state we can use, where these are the various forms of equations for each equation of state. Then further we had a look at this compressibility factor method, where we need the values of phi 0 and phi prime, and charts I showed you, Lee-Kissler charts. So from those Lee-Kissler charts, these phi values can be obtained directly for the component of interest. Similarly, using residual volume approach also, it is nothing but V actual minus V ideal. So if we plot the diagram of V residual by RT versus pressure, we can directly get this, but the only condition is we should know the PVT behavior in the entire pressure range of in interest. Okay. And then from enthalpy and entropy residual function, so we see that we need to know HR and SR. So ln phi is nothing but HR by RT minus SR by R. And the charts, Lee-Kissler charts or Lee-Kissler tables are available for this. Okay. So now let's try to understand what is fugacity coefficient in a condensed phase. Okay. So this is my standard generalized equation, that RT into ln F by P is equal to integration 0 to P minus RT by P dP. Correct? Zero pressure is gas phase. To, let's say I'm going in a pressure where the system is in liquid phase. So what is going to happen? I will be going from zero pressure to some vapor phase, then from vapor phase to vapor liquid equilibrium, and then to liquid phase. Okay, so what I will write? I will write that 0 to P set. How can I write this equation? RT ln FC by P is equal to integration 0 to P set V minus RT by P dP plus P set to P VC, that is condensed phase volume, RT minus RT by P dP. Now, when it is in equilibrium, fugacity of vapor phase will be equal to fugacity of liquid phase. That's why that term is not visible here, because we don't need to write it, because both liquid and vapor have same fugacities. Okay. So now how can I write this equation? This term is nothing but RT ln F by P, but in terms of F set divided by P set, because we are at saturation conditions, plus integration of P set to P VC into dP minus RT dP by P is ln P. So ln of P by P set. Correct? So this term we divided into two parts. One is VC and another is RT by P. So VC dP minus RT into RT by P dP, and RT by P dP is RT into ln P, and we have a limit from P to P set, P set to P, sorry. So we will have ln of P by P set. So ln FC by P is equal to ln of F set by P set minus ln of P by P set plus integration P set to P VC by RT dP. I'm just dividing whole equation by this equation by RT. So here RT cancels out. So we are only left with this. Here also RT is cancel out. We are left with this and these terms. Okay. So now, yeah, this till here we had a look. Now this P set will cancel out, right? So we'll be left with this particular term. So I can write this equation as Fc is equal to F set into exponent of P set to P Vc divided by RT into dP. And phi set is nothing but what will be phi? Phi is F by P. So what will be my phi set? Phi set will be equal to F set divided by P set. Okay, so I can write down as Fc is equal to P set into phi of vapor set into exponent of P set to P Vc by RT into dP. Correct. So this term, let's say I am integrating it, Vc by RT is common and integration of dP will be P, that is P minus P set. Correct. This term at low pressures. So it will be just P minus P set. So this term is known as Poynting correction factor. If P and T are not very high, gas anyway behaves ideally and we will have phi V set is equal to 1. Okay. For condensed phase where pressure is not very much far from P set. So what we can say that this P minus P set is approximately 0. We are dealing in condensed phase, but that condensed phase, it is not very far from P set. P is not very far from P. So what can we write? We can say that P minus P set is approximately equal to 0. So we will be only, if this term is 0, that exponent of 0 will be equal to 1. Okay, so Poynting correction factor will be equal to 1 and this is for not very high pressures. Okay, so if we see this condensed and incompressible substance, when P is equal to 1, this Poynting correction factor is 1.00405. When P is equal to 10, it is 1.0405. When P is equal to 100, it is 1.499. For 100, it will slightly affect our result. And when we will take Poynting correction factor is 1, and when P is equal to 1000, my Poynting correction factor is 57.9. So you see that when we are dealing at very, very high pressure, the Poynting correction factor is coming into picture. Okay. So 5V set, it differs from unity as we go near to critical temperature, and 5V set is less than 1 going to reduce Fc. And for low to moderate pressures, we know that for low to moderate pressure that 5V set will be equal to 1 from that equation, and we will have Fc is equal to P set. We will be only left with Fc is equal to P set and low to moderate pressures. So this term Poynting correction factor is going to be 1. Phi V set also equal to 1. So we will be only left with fugacity of condensed phase equal to vapor pressure of that particular system. Okay, so this is very important phenomena, fugacity coefficient for condensed phase, where we see from 0 to P set and P set to P, and we try to divide equation in parts, and we find that Fc is equal to P set into Pv set exponent of P set to P Vc by RT into dP. And this term is called Poynting correction factor. And when we are dealing with very low pressure, then this term is Poynting correction factor is going to be 1 approximately. And when we are dealing with very high pressures, then we need to incorporate this Poynting correction factor. And at very low pressures, that 5V set will be also equal to 1. This term will also be equal to 1. So we'll only be left with fugacity of condensed phase equal to vapor pressure. Okay. Now, one of the most important application of this is in hydrocarbon industries. And in hydrocarbon industries, generally Radlick Quank two parameter equation of state is used to estimate the fugacities. So from RK equation of state, this equation, I don't know if it is mentioned here in the way I want. Yeah, this equation. Okay, it is not the way we want, but yeah, this is the equation. This is the equation. P is equal to RT divided by V minus B minus A divided by T raised to 0.5 V plus B. It is same. This is my equation. Where is it written? Yeah. RT divided by V minus B minus A of T. What is A of T? For RK equation of state, that is square root of TR. TR is to 0.5. Okay, here it's not sorry, it is TR is to 0.5 into my epsilon is also 0 and sigma is 1. So I will be only left with V into this we have written 1 upon TR is to 0.5 V into V plus B. And what is going to be my A and B value? So what is my A? A is nothing but psi into R square DC square by PC. So what is psi for RK equation of state? Psi is 0.42748 R square DC square by PC. So it is 0.42748 R square. PC raised to 2.5 by PC and B is 0.08664 RTC by PC. It is here like this. B is my 0.08664 RTC by PC. Okay. So we write it down as what will be my VDP? VDP will be equal to differential of PdV minus integration of PdV. What is going to happen if I expand it? It is P of dV minus PdV minus VdP. So PdV term is additional. That is what I am removing. So this equation holds true. Then I need to replace PdV in that Fugacity equation. So PdV is RT integration dV by, if I put this equation, RT integration V minus VB dV of dV by V minus B minus A divided by T raised to 0.5 122 dV V plus B. So this is what we get from when we estimate this, and we need to do this equation Z minus 1 minus 1 upon RT dV. So if we do this 1 upon RT VdV, so we get this particular formula Z minus 1 minus ln of Z minus BP minus A square by P ln of 1 plus BP by Z. Something similar to what we obtained. The functional form is slight different. Okay. So we say that when I want to use this particular, let's say I want to use this particular equation of states to find phi. So one thing is very important to remember, that the Z value should be, let's say I want to use Pang-Robinson equation of state to find the values of Fugacity coefficient. So what I am supposed to do, I am supposed to find the value of Z also from Pang-Robinson equation of state. I cannot use phi for this Pang-Robinson equation of state, and I cannot use then Z with RK, SRK or any other equation of state. Whichever equation of state I am using, it should be consistent with calculation of Z also. So that is something very important to remember. So this is the simplified form for Z, Z cube minus Z square plus BP A square by B minus BP minus 1 into Z minus A square by B BP square equal to 0. When I solve this cubic equation, I find one Z will be very small, one Z will be very large. The small value will be related to saturated liquid phase, and largest value of Z will be related to saturated vapor phase. And we have already seen there will be one intermediate value of Z which has no real physical meaning. Okay. So this log F by P ratio is a function of RK parameters, which are A square by B and BP. So for that, in low and high range, values of A square by B and BP and low to high range, some plots are available in the literature. So when my BP is less than 0.20, it is called low range ratio. So for that BP, so what do I need to find? First, I need to find the values of A square by B and BP. That will give me the range. And from that, I need to read the chart, and that reading of chart will basically give me the value of Fugacity coefficient. Okay. One very important thing to remember here is RK equation of state is less accurate compared to Pitzer at all values in regions of coexisting vapor and liquid phases, but it is advantageous in being completely analytical and satisfying conditions of critical isotherm at critical point. So this equation can be used, but it has slightly less accuracy than what we use when we are dealing phi is equal to phi 0 into phi 1 raised to omega. So that is what we must remember when we are dealing with this. Okay, so this is all about the theory part today. So we first had a look at this heterogeneous closed system, and we derived the condition for thermodynamic equilibrium, that is temperature in each phase should be equal, pressure in each phase should be equal, chemical potential of each component in each phase should be equal. And we find that Gibbs phase rule F is C minus pi plus 2, where C is number of component, pi is number of phases, and plus 2. So this is what we use to find a Gibbs phase, find a variables. Now after that, what we did, we related in isothermal condition, we related change in abstract thermodynamic quantity chemical potential, which is simply the logarithmic function of physically real quantity pressure. Okay, then we tried to write it for real gas, and we found out that instead of developing so many correlations, we can just replace this whole term as ln f, that is called fugacity. Lewis defined it as fugacity, and this equation can be used for any component in the system, whether it is solid, liquid, gas, pure, mixture, ideal, real. For anything we can use this particular equation. Then these are very important question. Maybe these are asked in GATE. When my pressure is tending to 0, my fugacity coefficient phi tends to 1. And for the mixture, fugacity coefficient of mixture phi cap tends to 1. That is Fi by Yip. Okay. When I'm writing in terms of F by P, it is called fugacity coefficient. When I'm writing in terms of F by F0, it is called activity, which shows how active a substance is relative to its standard state. Okay. So then we had a look at various choices of standard states. Then we just try to interpret fugacity in terms of chemical potential is difficult to visualize, but fugacity can be convinced more easily as a corrected pressure. Okay, and these corrections were due to the non-ideality of gas, and we derived the relation between chemical potential and fugacity. Now, we had a look at this thermodynamic equilibrium condition in terms of temperature, pressure, and chemical potential. But now we have related chemical potential with fugacity. So how our thermodynamic conditions are going to change? So we derived it, and we found out as temperature in both phases should be same, pressure in both phases should be same. These two remains as it is, but the condition changed is fugacity of each component in each phase should be equal. Okay. Then we looked at the effect of temperature and pressure on fugacity. This was the effect of temperature, and this was the effect of pressure. Then we used another method, that is compressibility factor method, to understand that, and we found that we need to, from picture correlation, if we know phi is phi 0 into phi prime raised to omega, if we know that, we can directly estimate the fugacity coefficients from picture correlation. And for these, all the charts are available in the literature, and you can find those charts in any standard books, thermodynamic books. Then we used residual volume approach, where we need to plot VR by RT versus P. But one thing very important to know, that we must know the PVT behavior of gas in entire pressure range, where we are interested to calculate that. Then from enthalpy, entropy, residual function, we find that ln phi is HR by RT minus SR by R. And similarly, HR by RT and SR by R can be calculated from Lee-Kissler correlations that we had studied last week. So HR by RT, HR by RTC is equal to HR by RTC at 0 plus omega into HR by RTC 1. Okay, so if we do that, and similarly for SR by R, so we can find the value of fugacity coefficients. Okay, now when we are dealing with just condensed phase, so we found that we just need to, we found this particular equation that fugacity of condensed phase equal to P set into phi V set into exponent of P set to P Vc by RT into dP. And when we are dealing with very low pressure, not very high vapor temperature conditions, so what we can neglect, we can say that this Poynting correction factor exponent of P set by P Vc by RT dP, that is equal to 1, and PV set also is equal to 1, so we are only left with FC is equal to P set. And these are some data from literature that when we are dealing with very high pressure, then only this Poynting correction factor is coming into picture. Okay, then we had a look at RK equation of state, two parameter equation of state, which is generally used in hydrocarbon industries for estimation of fugacity. And for that, plots are also available. We need to find the values of A square by B and BP. Based on the range, we need to read the chart and we need to find the value of fugacity coefficient phi. Okay, even if this RK equation of state is less accurate compared to the pizza correlation, but still it is advantageous. Okay, so this is all what we had looked in today's class for the theory part. Let's try to solve some problem statements and then we will stop. Okay, so sorry. Yes, this is our first problem. Problem statement says that reported values for the virial coefficients of isopropanol vapor at 200 degrees Celsius are B is equal to minus 388 centimeter cube per moles and C is equal to minus 26,000 centimeter raised to 6 per mole square. So we need to find the values of V and Z for isopropanol vapor at 200 degrees Celsius and 10 bar. Okay, so first we are going to use ideal gas state. So what is it going to be for ideal gas state? For ideal gas state, volume V is equal to RT by P. So R, T and P we know. So for ideal gas condition, we need to find both values of V and Z. So for ideal gas, Z is anyway is equal to 1. And for ideal gas, volume is RT by P. So I'm just putting R as 83.14. Temperature is this 473.15, that is 100 degrees Celsius. And pressure 10 bar. So this is my ideal gas volume that I'm getting. That is very straightforward and very simple. Now for the second part, sorry. Z, this relation I am supposed to use, which is Z is equal to 1 plus BP by RT. Okay, so I will use Z is equal to 1 plus BP by RT to find the value of Z plus Z first. I can do anything. So what I did, I replaced Z as PV by RT is equal to 1 plus BP by RT. So my volume will be equal to RT by P plus B. So RT by P, R is 83.14. Temperature is this 473.15 and this pressure is 10 minus B, that is given to us as 388. Okay, let's just check. Let me check one thing from these tables. Yeah, value of R is 83.14 in terms of centimeter cube, so we are fine. Okay, so we don't need to change it because when we are taking 83.14, it is volume is in terms of centimeter cube per mole and pressure is in terms of bar. Okay, so 3933.77 minus B was 388. So my volume is coming out to be V is equal to 3545.17 centimeter cube per mole. Now what is Z? Z is my actual volume by ideal volume. So actual volume is this 3545.17 and my ideal gas volume is 3933.77. So that ratio is coming out to be 0.9012. Now for this third equation, Z is equal to 1 plus B by V plus C by V square. Okay, so when I am writing this, Z is equal to 1 plus B by V plus C by V square. So V is not known to us, Z is also not known to us. So what we do, we first replace Z with PV by RT. Okay, so my V will be equal to RT by P into 1 plus B by V plus C by V square. So, okay. So what we are seeing here, V is on both the sides. So we need to solve this equation iteratively. So let's try to solve it in Excel. How can we do it? So here we see that our temperature is 473.15 Kelvin and pressure is 10 bar. This constants B is equal to minus 388 and C is equal to minus 26,000. Okay, so what is my equation? So my V is equal to, let's first find one terms, RT by P, that is equal to R is 83.14 into T 473.15 divided by P. Okay, so this is my ideal gas volume. So it is RT by P. Let's say I'm doing first iteration, I is equal to 0. So I will be finding the value of V. So it will be equal to RT by P into 1 plus B by V plus C by V square. So 1 plus B divided by, I'm starting with this initial volume, V, 1 plus B by V plus C divided by V square. Okay. And this RT by P term will always remain as it is. B will also remain as it is. And C will also remain as it is. Sorry. Okay. So when I'm taking first my gas as ideal gas volume, I'm getting this number. Now for my second iteration, yeah, this just I need to change. My initial gas of volume is this term. This is what I get, and if I extend it, so I find that after some iteration, I'm getting constant volume of 3487.742. I need to check this with book. So it is 3.8, page 94. 3488 centimeter cube per mole. That is what we are getting. 3487.854. That is approximately 3488 centimeter cube per mole. That is what we are getting. So if we just extend more digits, so we see that volume is not changing as I am increasing my iteration. Let's say this is my first iteration, second iteration, like that. So you see within some this iteration, 5 or 6 iteration, we have achieved the value. So if we see the difference between earlier value and new value, so see first it was 44. See, if we keep increasing, the difference is going to be very less, but that is not going to make any kind of sense because we have anyway achieved the difference very less. See, after some one point, the difference is approximately 0, and we don't need to go till there. After so many iterations, because our point is conveyed within this particular error bar. It is coming out to be approximately 3488 centimeter cube per mole. Okay, so this is how we can solve for Z and V. So now for this value of what will be the value of Z for this? My Z will be equal to actual volume, that is this, divided by ideal volume, that is this. My Z is coming out to be 0.8866. Okay, here I have made some mistake, but yeah, that is the exact answer that I have shown it to you. It is 0.88. Okay, let's try to move ahead. Sorry, where did it go here? Yeah. So, okay, let's try to take next problem. Okay, this problem we will solve in next class. For this, we will require MATLAB. So I will show you this problem in next week. Let's take this problem. Okay, so air is compressed from an initial state of 1 bar and 298.15 Kelvin to a final state of 3 bar and 298.15 Kelvin by three different mechanically reversible processes in a closed system. Okay, so I am compressing my air from initial pressure P1 is equal to 1 bar, T1 is equal to 298.15 Kelvin to a final state which is 3 bar and 298.15 Kelvin via three different routes. The first route is heating at constant volume followed by cooling at constant pressure. So heating at this is V. So heating at constant volume followed by cooling at constant pressure. So this is the one way I am reaching this route. Second route is, I'm sorry, isothermal compression. So I am directly going from 1 to 2 via isothermal compression. Then the third route is adiabatic compression followed by cooling at constant volume. So this is my adiabatic compression and then I am cooling it at constant volume to reach my desired temperature. Okay, so what we are supposed to find for this problem. So these processes are shown in the figure that we already look. We assume air to be in its ideal gas state and assume constant heat capacities. Cv of ideal gas is 20.785 and Cp of ideal gas is 29.1. So here we are assuming that Cp and Cv are not function of temperatures. Okay, they are constant in our temperature range. The calculated work required, heat transferred, and changes in internal energy and enthalpy of the air for each process. We are supposed to find delta U, delta H. Okay, so from our first week lecture, let me open that. For ideal gas, for ideal gas, yeah, this thing. For ideal gas, we know that du is only function of temperature. So du is nothing but CVDT for ideal gas and dH is nothing but CPDT for ideal gas. Okay. So now we know that for our system of interest, for all paths that we are following, uh, starting temperature is also 298.15 Kelvin and final temperature is also 298.15 Kelvin. So as there is no temperature difference, there will not be any change in internal energy and there will not be change in enthalpy irrespective of any path we are following. So first thing we say that delta U is equal to 0, delta U is CVDT equal to 0 and delta H is equal to CPDT, that is also equal to 0 as there is no temperature change. Now further, the first process is heating at constant volume. So first I am going to heat at constant volume. So what can I write? As I am heating from here to here. So I will have some different value of temperature. So that temperature, let's try to find out. So it is P1 by T1 is equal to P2 by T prime. Let's say I'm calling this temperature as T prime. So P1 is 1 bar, T1 is 298.15 Kelvin, P2 is 3 bar, T prime we are supposed to find. So T prime is nothing but 894.45 Kelvin. Okay. So when I am dealing with constant volume, heating at constant volume, so my Q1 for this particular 1 to 1A. So my Q1 is nothing but CV dt. Q1 is equal to delta U is equal to T1 to T prime CV dt. So my CV is 20.787 and delta T is final temperature, that is 894.45, and initial temperature 298.15. So I get Q1 is equal to 12394.1 joules. Now what will be my W work done by the system? That is minus PdV. Now I am heating at constant volume. So my volume is delta V will be 0. So my W1 will be equal to 0. And for this stage when I am cooling at constant pressure. So for cooling at constant pressure, Q2 is equal to S when I am dealing with constant pressure. So my Q2 is delta H is equal to Q2, that is integration of from here T prime to T CPDT. So 29.1 final temperature, that is 298.15 minus initial temperature, that is 894.45. So I get Q2 as minus 17352.33 joules and W2 as minus P delta V. So my pressure is 3 bar and delta V volume change. Initially my volume was, okay, so let's try to first find out initial and final volumes. So my initial volume was V1 is RT1 by P1, that is 0.02479, and V2 is RT2 by P2, that is 0.008263 meter cube. Okay, so important thing, as we are here in this part, calculations are in SI units, so I need to convert bar to joule. So I need to multiply with 10 raised to bar units to joule units. So I need to multiply it with 10 raised to 5. So I get W2 is equal to 4958 joule. So as you know by intuition that this is iso, final and initial temperatures are remaining same. So if I find delta U is equal to Q plus W, and as delta U is 0, my Q should be equal to minus W. So let's try to verify it. Q is equal to Q1 12394.1 plus Q2 minus 17352.33. That is coming out to be minus 4958 joules. And W is equal to W1 plus W2. W1 is 0 and W2 is coming out to be 4958 joules. So Q is equal to minus W. That is what we are trying to satisfy. So not we are trying to satisfy, we are getting it by its own. Okay. Now let's try to follow the second path, that is isothermal compression. I am directly going from 1 to 2. Okay, so how can I, for that process, for any isothermal process, we have looked this into our first class that, sorry, where did it go? Yes, here for any isothermal process, my work done by the system is W is equal to integration of minus of PdV minus V1 to V2 PdV. So minus V1 to V2, my P is RT by V dV. So minus RT ln V2 by V1. So for isothermal process, PV is constant. So P1 by V1, P1 into V1 is equal to P2 into V2. So I can replace V2 by V1 as P1 by P2. Okay, so what will be my work done for this system? W is equal to minus RT ln P1 by P2. So I can just write it, W is equal to minus RT ln P1 by P2 minus R 8.314, temperature to 98.15, P1 by P2 I am going from 1 bar to 3 bar. So 1 by 3, as it is ratio, it doesn't matter if I multiply with 10 raised to 5 or not at both places. So my W I am getting is at minus 2723.26 of joules. Okay. we know delta U is Q plus W and delta U is equal to 0. So therefore Q will be equal to minus W, that is 2723.26 Joule. So for this process, isothermal process, heat is needed to be added in the system. Now the third path that is told to us as isothermal compression followed by cooling at constant volume. So this is my isothermal compression where I am going from 1 to C and followed by cooling at constant temperature, cooling at constant volume. So let's first try to find out for this isothermal compression route, adiabatic compression. So for any adiabatic process, PV raised to gamma will be equal to constant. But here what we are saying that we are trying to do adiabatic compression, right? So for this adiabatic compression, temperature is going to change. So I will write this equation not in terms of PV, but I will write it in terms of T comma V. So I can write it down as TV raised to gamma minus 1 is constant. So T1, V1 raised to gamma minus 1 is equal to, let's say, this temperature here is T star. So T star V raised to gamma minus 1. V2 raised to gamma minus 1. So T star will be equal to T1 into V1 by V2 raised to gamma minus 1. Now, what will be the value of gamma for an ideal gas? So this we have looked at here, that for any ideal gas, gamma will be equal to Cp by Cv. Okay, and we are given the values of Cp and Cv, where Cp is equal to 29.1 and Cv is equal to 20.787. So gamma is 1.4. So my T star will be equal to T1, that is 298.15, V1 by V2. That is nothing but if you take this ratio of V1 comma V2, V1 to V2, if you take this ratio, it is coming out to be 3. So V1 by V2, that is 3 raised to 1.4 minus 1. So that is nothing but 462.68 Kelvin that I am achieving. Okay. Now, as it is adiabatic compression, my Q1 will be equal to 0. And I need to find the value of W1. So from the first law of thermodynamics, delta U1 will be Q1 plus W1. Now Q is equal to 0. So delta U or W1 will be equal to W equal to delta U, that will be CV dt. So that is CV is 20.785 and dt. So it is T1 to T star, that is 462.68 Kelvin minus 298.15 Kelvin. So W1 is coming out to be 3419.76 Joule for this particular process, this path, adiabatic compression. W is this and Q is equal to 0. Q1 equal to 0. Now we will follow cooling at constant volume. Cooling at constant volume. So for cooling at constant volume, as it is constant volume, so W2 will be is equal to 0. And when W2 is equal to 0, and as we are dealing with constant constant volume, so my Q will be equal to delta U, that is Cv dt. So integration T star to T Cv dt. So it will be just negative of this minus 3419.76. So what is my Q? Q is equal to Q1 plus Q2, that is minus 3419.76. And my W is equal to W1 plus W2, that is 3419.76. Okay. So in all cases, my Q and W's are different. In all cases, heat is released, but we know that Q and W are path function, they are not state function. So for this, each individual path, the values of Q and W are coming out to be different. Okay, so let's try to take one more problem and then we will stop. A central power plant rated at 8 lakhs kilowatt generates steam at 585 Kelvin and discards heat to a river at 295 Kelvin. Okay, so the rating is given as 8 lakhs kilowatt and it generates steam at 585 Kelvin and it discards heat to a river at 295 Kelvin. If the thermal efficiency of the plant is 70% of the maximum possible value, so what is called the thermal efficiency of plant is 70% to what is maximum value. So what is the heat discarded to the river? Okay, so this is the clear problem of second law of thermodynamics. So this we have looked at here, that for any cycle, an efficiency cannot be more than the Carnot cycle. So what is told to us, that in problem what is told to us, that 70% of maximum possible value. So what will be my maximum possible value? My maximum possible value of efficiency is for Carnot engine. That is from second law of thermodynamics. That is what it is stated. So when we find the value of efficiency, so efficiency comes out to be 1 minus Tc by Th for Carnot cycle. Okay, no engine can have thermal efficiency higher than that of a Carnot engine. So what we need to do, we need to first find out the efficiency when we are dealing with Carnot cycle. So Tc is 585 Kelvin. Sorry, Tc is 295 Kelvin and Th is 585 Kelvin, and eta is zero point 0.7 into eta Carnot. Here it's a mistake. I need to write into eta Carnot. Okay, and W rating is given as 8 lakhs kilowatts. Okay, so what is going to be my eta Carnot? Eta Carnot is 1 minus Tc by Th. So 1 minus 295 by 585, that is 0.4957. So you see, Carnot engine is only giving maximum of 50% efficiency. So what is told to us, that for actual thing it is 70% of maximum efficiency. Okay, so my eta actual will be 0.7 times this value. So that is just 35% efficiency. Okay, so my eta star is 0.34699. Now what is told to us to find out how much heat is discarded? So when we had a look at the derivation of this thing, so efficiency is defined as work done divided by heat discarded. So my work done is nothing but QH minus QC divided by mode of QH. So I am writing it eta star is equal to W by QH. So W is 0.34699. Sorry, eta star is 0.34699. That is equal to W, that is 8 lakhs kilowatt divided by QH. So QH is coming out to be 8 lakhs divided by 0.34699. That is coming out to be 230. That is coming out to be 2305541.95 kilowatts. Now what will be my W? Sorry. W will be equal to, more W will be equal to this mode of QH minus mode of QC. I don't want to get into trouble of positive negative signs. That's why I'm writing in terms of magnitude. So 8 lakhs will be equal to QH minus QC. So heat discarded will be minus 1505541.95. Negative sign indicates that heat is discarded to the atmosphere. Okay. So this is what we had looked today. Sorry, where did that end? Okay, so that is what we were supposed to find out, how much heat is discarded to the river at rated power. So the only thing to remember here was the maximum possible efficiency value is only for Carnot cycle. So we need to find that at a value for first for Carnot engine, and then we need to multiply it with 0.7. In this problem also, we need to be very careful with the units and its conversion. So it can be you guys can be tricked in your exam with units. So just just make sure that whatever units you are using, those units are consistent throughout. Okay, so these two problems about entropy change, this we will be keeping for our next class. So in today's class, what we had a look at first, we derived the thermodynamic equilibrium conditions in terms of temperature, pressure, and chemical potentials. We derived that Tp and mu for each component and each phase should be same. Then we derived the Gibbs phase rule, that is C minus P plus 2. Then after that we tried to understand the concept of fugacity, which is measure of non-ideality of gas. And instead of deriving mu d mu in terms of, it was RT d of ln p, for real gases, we just replace P with F. Then we try to find out how fugacities can be derived using equation of state. How can we calculate it using equation of state? Then compressibility factor method, where we looked at Lee-Kissler chart. Then from residual volume, where we need to plot VR by RT versus pressure. And then we had a look at residual enthalpy and residual entropy approach, and that HR by RT and SR by RT that we can calculate from Lee-Kissler charts available into the literature. Then after that, we had a look at fugacity at condensed phase, and we find out that Poynting correction factor is equal to 1 at very low pressures. So when we are dealing with not very high pressures, then Poynting correction factors can be neglected. And then we try to find out fugacity by using RK equation of state, that is most practical for hydrocarbon industries. And there we see that if we know the values of A square by B and BP, then charts for RK equation of states are available, and from there fugacities can be estimated. And the very important thing to remember was, when we are dealing with equation of state, so let's say if I'm willing to find the fugacity of system with using RK equation of state, then in that equation Z should also be estimated from RK equation of state only. I cannot use any other equation of state, or I cannot combine. And then we try to look at some particular problem statements. Okay. So if anyone is having any query, please feel free to write me on this email ID. I will try to respond to your query as soon as I can. So thank you so much. We will meet on next time.